Let's look at one more example of using spherical coordinates to evaluate an integral. Let's evaluate this triple integral. So these crazy bounds essentially mean we're integrating over all of 3D space, right? All of R3, right? Because x, y, and z are both going from minus infinity to plus infinity, so that's going to cover all of 3D space. And this integrand looks pretty wild, but because the variables always show up in this combination, x squared plus y squared plus z squared, well, that's just going to be rho squared, right? Rho squared is x squared plus y squared plus z squared. So if we use spherical coordinates, this integrand will actually not look that bad. Also, in spherical coordinates, we can express all of 3D space. Right? 3D space is essentially like a sphere with an infinite radius, and we know we can cover spheres with spherical coordinates. So, and of course, this part dv, we know how to write dv in spherical coordinates. So this looks doable in spherical coordinates. So now that we have the idea to use spherical coordinates, let's dive in and actually do it. So let's start with our bounds, I guess. dv is rho squared sine phi d rho d phi d theta. Okay, so for our theta bounds, right, remember we're kind of treating 3D space as an sphere with infinite radius. So what theta values do we need to cover this sphere? Well, we have to go from theta equals 0 all the way around to theta equals 2 pi. So from 0 to 2 pi. What phi values do we need? So remember, phi is measured from the positive z-axis. So we need to start going directly up, and then to get all of the sphere, we have to go from directly up all the way down to directly down. So that's from 0 to pi. And then for rho, we have to go from the origin, that's at rho equals 0, out to, well, to cover all of 3D space, we're going to get infinitely far from the origin, so rho has to go all the way up to infinity. Well, not to infinity, but it has to approach infinity. So these are the bounds that we get for rho, phi, and theta. Notice that with spherical coordinates, only one of our integrals has an improper bound, infinity, and it's only improper on one side, on the top bound. Right? Our original integral every integral had improper bounds on both sides, which is especially inconvenient. Okay, so now let's rewrite our integrand. So square root of x squared plus y squared plus z squared, well, that's rho. And then e to the minus x squared plus y squared plus z squared, that's rho squared. All right, and as so often happens, our integrand is now a product of a function of rho, a function of phi, a function of theta, so we can separate our integrals. So this is for theta, that's integral from 0 to 2 pi of, well, there aren't any thetas in our integrand, it's just d theta. For phi, that's the integral from 0 to pi of, phi only shows up in sine phi, so sine phi d phi. And then for rho, that's going to go from 0 to infinity. Remember, an improper bound like this really means this is a limit as the top bound goes to infinity, but I'll let you worry about that. So this is going to be rho cubed e to the minus rho squared d rho. All right, so this theta integral, that's pretty routine, right? That's theta from 0 to 2 pi. That's going to give us 2 pi. This phi integral is going to give us minus cosine phi from 0 to pi, so also pretty routine. This rho integral, this is not as pleasant, right? This looks annoying. So I mean, since we have powers of rho down here and also up in this exponent, To me, that feels like maybe we want to do a u substitution and let u be this exponent. So minus, or maybe, actually, let's keep it plus. Let's not absorb the minus sign into u. So u equals rho squared. So du is going to be 2 rho d rho. So, okay, so when rho is 0, so now working on our bounds, when rho is 0, u is also going to be 0, so our bottom u bound is 0. And when rho goes to infinity, u also goes to infinity, right? Because rho squared goes to infinity, so our top bound is still infinity. So now, let's see. So let's see, we can take one of these factors of rho and absorb it into, combine it with d rho to get du over 2, right? So what I'm saying here is du over 2 equals rho d rho. So I'm taking a factor of rho, combining it with d rho, and I get du over 2. That leaves me with 2 factors of rho, but 2 factors of rho, that's u, so u, times e to the minus rho squared, but that is also u. Okay, this looks good because this is something that we can handle with integration by parts. Okay, so let's see, we have this over 2 way over here. Let's use that to cancel this 2 all the way out front. So we get a pi. And now for our phi integral, when we plug in pi, we get minus minus 1, so that's 1, minus another minus 1, so that's plus 1. So this all is going to turn into 2 times, now we have to work out this integral. So again, integration by parts. For integration by parts, we're going to use u, the derivative of u is 1, and we're going to use e to the minus u, and the integral of e to the minus u is minus e to the minus u. So we get minus u times e to the minus u, minus the integral from 0 to infinity. Oh, I need bounds here. This is from 0 to infinity. Okay, minus the integral from 0 to infinity of 1 times minus e to the minus u. Minus e to the minus u, du. Okay, so here we have 2 pi times. Okay, now when we plug 0 into this, clearly we're going to get 0, but what about the limit as u goes to infinity? Right, this actually gives us an indeterminate form because this u part is going to infinity, but e to the minus u is going to 0.